So today I'm going to see how far, I hope I can finish everything I want. So I'm going to start by proving Turin's theorem. So remember, the Turin's theorem is showing that if you have a graph on n vertices, avoiding a clique of size r plus 1, then the maximum number of edges is going to occur exactly when you get this Turin graph, which is an r-partite graph, complete partite graph, where all the parts are equal. And this is the only graph that will hold the property. So I'm assuming, or I hope that they teach equivalence relations in 250. So I'm just going to redefine the definition of equivalence relation. We're actually going to prove this using the concept of finding some way of defining an equivalence relation on a graph that holds the property of having the most number of edges, and then we're going to show that it's exactly going to look like this. So remember, the three conditions are being reflexive, symmetric, and transitive. So to prove this, we're going to let G be this graph that holds the property of having the most number of edges. And then we're going to define this relation that we're going to prove is an equivalence relation to kind of force that, well, if it is the maximum possible number of edges in the graph, it's going to force or restrict some structure by using this equivalence relation. So technically, it is, I would say, pretty logical once you show that it's a, I guess, general p-partite graph, that it will be optimized whenever the parts are the most equal and the value, it's broken up into r parts. But I'll give a little more, I guess, brief explanation on that. So what we're showing first is just that it will be a p-partite graph, but we then have to verify that the best possible case is exactly whenever it's broken up into exactly r parts. So we're going to define this relation on the vertices, the set of vertices, kind of in the opposite manner of how we naturally would, in a sense, define a relation on a graph. So I'm going to define a relation between two vertices whenever they're not adjacent. So the hardest part to understand of this argument is, I would say, understanding this equivalence relation is proving transitivity. So the first two cases should be very, very obvious. And so again, this graph is obviously simple, so there are no loops in the graph. So obviously x is not adjacent to x, it's not adjacent to itself. And then given for the second condition, right, if I tell you A is not adjacent to B, well, then obviously there's no edge between them. So obviously B is not adjacent to A. Right? So the first two conditions are very simple to follow. The third one is a little more difficult to follow, and kind of the logic of how it flows is a bit confusing. So for the third part, what we're saying is that, well, okay, if I know A is not adjacent to B, and I know B is also not adjacent to C, you want to conclude then that also A is not going to be adjacent to C. So the logic of how this is going to flow is, I'm assuming that X can be adjacent to Z, which would then violate transitivity. But what we're going to show here is that, well, if you do tell me that X has to be adjacent to Z, or it's possible that X is adjacent to Z, then I'm going to show you that the graph you just told me doesn't actually have the maximum number of edges, which is a contradiction. Because we're assuming that this graph that I'm looking at is already going to be the chosen one that has the maximum number of edges. And it should logically make sense that here, well, if I can show that somehow I can manipulate the graph and then have even more edges, well, then that's contradicting the assumption that G was the most. And obviously I can't keep doing this and keep adding edges forever, right? Otherwise I would have the complete graph. So the goal here is that I'm going to show that if I were to have this adjacency here, I can then force the graph to have even more edges, which would be a contradiction on the assumption of how I chose the graph G. So there's two different cases. The arguments are pretty similar. Is that I have to compare and determine which one, whether or not the vertex Y has the highest degree amongst these three or not. So understand that visually, this is what we have so far. So what we're trying to conclude is that these three vertices won't have any edges among them, but we're assuming to the contrary, no. This graph that has the most number of edges does have an edge here. And so the goal is I'm going to show that, well, if that were the case, I could have constructed a graph even with more edges than the graph G. Oh wait, sorry. I should not be saying. I should include Z. I'm sorry. This is not this case. So, sorry. It just joins to everything. So understand that here, x and x prime are not adjacent. But now I'm creating this new vertex x prime that's going to join to everything else that x did. Sorry, I wrote the logic slightly backwards here, I realize. Sorry, I skipped one line here. The logic should go in the other direction, obviously. So what I'm saying here is that if the vertex for y doesn't have the max degree amongst the three, because it does not have the max degree amongst the three, there must be one of the vertices at least that has larger degree. So suppose that it's x, right? So therefore, suppose that the degree of x is larger than the degree of y. And then with that information, let me delete y and then replace it with x prime. And it'll join to everything else that x did. And so that's kind of the key thing, is that now it should make sense that if I'm replacing x with x prime, or sorry, I'm replacing y with x prime, the degree of y was less. So now I'm replacing it with x prime, which is joining to everything in x. So it should be clear here that this graph now has more edges. So, okay, this doesn't contradict anything at this point, right? Because you may say, okay, great, you do have more edges, but so what? That doesn't mean that you are actually creating this graph that still avoids a clique of size r+1, right? Sure, you can add more edges to the graph, but at this point, this doesn't violate anything, because just when you add more edges, you could claim now then I've created a graph that does have a clique of size r+1, which means then G originally was still the graph that had the most number of edges. I don't know if anyone sees, like, what's the logic here that's going to give us the contradiction. So I replaced this original vertex y with this x prime, and now I do have more edges. So if this doesn't contain a clique of size r+1, then yes, I have a contradiction, because then this has more edges and it still avoids a kr+1. But the thing is, you may say, okay, well, that doesn't have to necessarily be the case. So if this thing did have a click of size r+1, well, what happens then in the original graph, right? So if you think about if this new graph had a click of size r+1, right? By this picture, well, how would it have formed? What I did is I replaced y with x prime. Right? So necessarily, right, this click had to involve x prime. Right, because that's the only edges that I kind of added to the graph is formed from the x prime. So now if you told me in this new construction there is a click of size r+1, but then what's the issue here? So from the picture, right, x prime is the one that's having some effect to create this click of size r+1. But understand that what is x prime adjacent to? It's adjacent to everything exactly that x is by how we define this. And remember that x prime, there's no edge between here. I just deleted the y and put an x prime. So if you're telling me that there's a click here containing x prime, well, x had the exact same adjacent edges, or sorry, vertices as x did. But then what you would have been saying then, if there was a click of size r+1 containing x prime, I could have switched x prime and just chosen x, and there would have been a click in the original graph also. Right, so by switching that and working with the vertex x instead, you would have said the original graph that we started with G would have had a click of size r+1. So now we conclude that we have a contradiction here, because then you would have said, okay, G originally was the graph with the most number of edges, avoiding a k r+1. You just told me that, well, this entire argument, I couldn't have had a k r+1, but then this would have said at the end that you've constructed some graph that has even more edges than G, or so, than this original graph. Does anyone have a question on that so far?
Yeah, so when you mentioned how if there's now a click in the new graph, it must include x prime. The reason behind that is that we just took out y and added x prime, and now that there's a click, the click must involve x prime.
Yeah, because those are the only new edges that you formed must have been coming out of x prime. So what you said is correct. I don't know if that's what, but I'm not sure if that's what you're asking or you're telling me.
Yeah, I guess I was just asking that.
Yeah, because if you do have a click, we should agree that when I switched the two things, the only new edges that I'm making must have been incident to X prime. So this new clique that I formed must have involved X prime, because otherwise I would have just deleted X prime. And if you said there was still a clique, then there would have had to been a clique in the original graph G also. Right. So the new clique that that would have been formed had to have used at least some of the edges coming out of X prime, meaning that X prime was involved as part of the clique. Does that
Gotcha.
make sense?
Makes sense. Yeah.
So the second case, the argument is very similar. That you would basically either construct it so that there are more edges, or if you said, well, I formed more edges and now I still don't, or I form a clique of size r plus 1 would have forced a clique in the original graph G also. So this is going to be sort of strange, is that we're going to get rid of X and Z and replace it with two other vertices. And so we're going to claim here that, again, if you do this, the number of edges will increase. And you should be able to kind of see from this picture, if you follow this argument, the same thing's going to happen here. So I will explain why that is increased in a second, but you can now picture again, remember that now y prime, and y double prime, right? There are no edges among these three vertices. So in this new graph, if the number of edges increased, right? And if somehow a clique of size r plus 1 formed, again, by how this is constructed, right? Then you could have said, for example, that y prime was one of the vertices that helped form this clique of size r plus 1. But again, y prime has the same set of neighbors as y. So then instead of working with y prime, which you claimed was creating the clique, I could have chosen y to be part of it instead, because they have the same exact neighbors. But then you're saying in the original graph here, there would have been a clique of size r plus 1. So the same argument is going to kind of follow once we make this conclusion that the number of edges in this graph increase. All right, so this should be pretty obvious because we said that the degree for y is the largest. So if I'm replacing the x with y prime and it's joining to all the neighbors of y, right? This y prime is going to have the same degree as y. So you could technically say it's greater than or equal to in case they all have the same degree. But the key thing is that if I'm replacing it and y prime is joining to everything in y prime has the degree of y. So it must be at least as large as x, since you assume that degree of y was the largest. And so the little thing to recognize here is that when you're looking at these neighbors, right, how much did I delete? Well, you could say, well, then isn't nothing changing because you said it isn't d of y prime and then d of y double prime. They could have been equal to the degree of x and z. So the number of edges coming out should be the same. But that's the key thing is by this picture, right? The degree coming out, right, wouldn't have been different edges. Because the one coming out of x here, one of the degrees coming out is the same exact edge as the one of the degrees coming out for z. So again, what you have to make sure you're not deceived by is, right, the neighbors of this, if this was x, this is not going to be correct to say it looks like this. I would agree that the total edges removed would have been this if they completely looked disjoint like this, right? That's how many edges you would have lost replacing x and z with y prime, y double prime. But the key thing is they share an edge here, so therefore you lose one in the degree. Right, so therefore the number of edges must have increased. And now the argument is very similar. Okay, you've just constructed a new graph that has even more edges than the graph G. And you may say, okay, that's fine. There's nothing wrong with that. But if there's a clique of size r plus 1, as I just said earlier, well then, suppose that it was created by y prime. It involved y prime, since those are the new edges you're forming, similar to this argument. It's not adjacent to y or y double prime, so that those can't be part of the new clique that you form, right? Everything is adjacent. So if y prime is involved in this new clique, well, y prime has the exact same neighbors as y, so why don't I just, instead of choosing y prime, let me choose y instead to create that clique. But then in the original graph, G, you would have had a clique of size r plus 1. So this was a pretty long argument, but that's the key part now. Visualizing why this is basically the proof is the hard part. So I will kind of go, I guess, a little to the algebra argument. But understand that what we've concluded so far, right, is that, where did I find this? That our relationship x related to y when they're not adjacent. So this argument here, right, x is not adjacent to y and y is not adjacent to z. We assume to the contrary that x is adjacent to z, and we reach the contradiction in both cases. So therefore, this is telling me that x is not adjacent to z, so I satisfied transitivity. And so now what you're picturing is you can look at the equivalence classes of this equivalence relation, which exactly form the partite sets of the graph. But now, so it should be obvious that if you have an equivalence class, right, the things are all related, right? By how we define the relation, then there's no edges among those vertices. And now if you think about what's going to happen here, well, you can say, okay, great, you did partition this, I don't really care, that doesn't really tell me anything now up to this point. But now, if you think about it, if I see an edge here, right? If you're saying, well, that could be the graph and that's the best we can do. Well, what's going to be the issue here? If you're just telling me I'm just drawing that one edge, then what we have here, right, is that this vertex and this vertex are not adjacent if you're missing anything between here. But clearly, right, in the equivalence class here, nothing's going to be joining because they're related, right? So there's no edge here. But if I'm missing any edge here, right, well, what you just told me is this can't happen. It's transitive, right? So if I'm missing this edge here and missing this edge here, there can't be an edge here either. Equivalently, either you're saying one of two things. Either, well, then there are no edges, so therefore they should have been merged to one class. Or to avoid this property of transitive, or to make sure it is transitive, right, I would have to put an edge here. So what you're saying now is that this equivalence relation is forcing adjacency between any two different equivalence classes. There must be an edge going between all the vertices. This is, again, what we're seeing here, right? This picture is impossible to have because then these two vertices are not adjacent. By transitivity, this edge should not have been here. But if there's no edges amongst them, then I should have just merged this into one class because there's no edges. And therefore, the only way to avoid this is then there should have been an edge joining here. And you're basically saying there must be adjacency between every two vertices in all the equivalence classes. So this can't happen. It would have to force this other edge. Right, and so therefore we've shown that this graph must be p-partite and complete. And so from here, it's more just like algebraic argument. To show that, of course, the value of p that you want is going to be exactly r, and then everything should be as equal as possible. So I'll just kind of briefly write this, the last part of the argument. So it should be obvious that this choice of p has to be less than or equal to r. If it's r plus 1, then I would form a clique since everything's adjacent. Right? Right, so it should be pretty clear pictorially, or just using your own logic here, is that, well, if I had fewer than R parts, right? Well, what I could always do is let me just split it up, right? If these two vertices are adjacent to everything like ni number of vertices here, well, then clearly, right, what I could do instead right, this is still going to form two times ni number of edges, just like I had in here. But now, if I split this up, I'm going to create at least one extra edge here. And so the last part that you can argue here is that, okay, great, it is an R-partite graph, and you might be able to see, or you can prove it probably by calculus, that this is going to, the number of edges going between the parts will be as large as possible, right, whenever the parts are as close as in size as possible. So just to briefly verify it, so if you had these two parts, and then suppose that the difference in these two parts was at least 2 instead. Right, so all we have to show is that this value is going to be even larger, obviously, if I shift 1 over and make this like n1 plus 1, and then this one n1 plus n2 minus 1. This would have been in the original form, but if I shift 1 over and make it more balanced, then the number of edges would increase. You can either easily check that inequality. And therefore, we've proven that this graph G must be R-partite, complete R-partite, such that every part is differenced by at most 1, which is the Turing graph that we claimed at the beginning. Use NP and R. Right, so that was a pretty long proof. Does anyone have a question on anything on
that? Why is P clearly less than or equal to R?
Because if this was R plus 1, right? If there are R plus 1 parts, everything's joining here, which is exactly a clique, right? Because each part, if you could just imagine each part being one vertex instead. Right, but then that would be exactly forming a clique of size R plus 1. Is that
right?
Right, it's kind of deceiving from the picture, right? Let's just keep it really simple. Even if it was like this, well, I can just pick this vertex, which is joined to this, which is going to create a K3. Right? Is that believable? No.
So you're saying we need to avoid a K R plus 1?
Correct. So I'm saying that if you had R plus 1 pieces, like the partite, there were R plus 1 parts. then I can just choose one vertex in the R plus 1 parts. Being complete, it joins to everything else. So that is a K R plus 1.
Okay, I see.
Right? You're just being deceived that you have this blob, but just understand you can just take one vertex, and then now you basically have R plus 1 vertices from each blob. And that by complete R partite graph, they join to everything else. So it's a clique. Is that believable?
Yeah.
Okay, so naturally thinking about this in terms of, I guess, a research perspective is, okay, Turin's theorem, great. It proved it for cliques. Mantel's theorem was looking, I guess, at the K3 case. So therefore, Turin solved the generalization for any size clique to maximize the number of edges. But then we can actually also think about this, right, to look like a cycle on 3 vertices. So therefore, what if I want to extend this, right? Look at the most number of edges, avoiding all the cycles up to a certain size. This was avoiding a clique up to a certain size. Right? Because obviously if it doesn't contain a K10, it won't contain a K9, etc. And so, right, how hard can this question be? Well, it is very, very difficult. So we look at the case, let's try and avoid a 3 and 4 cycle. So there is a bound on this. The, I guess, final solution to this, though, of like, unlike Turin's theorem, where, okay, then the graph is unique, the question of like, when you get this to be best possible is sort of not exactly fully solved. It may be fully solved just because of last month, but it is not certain whether it's actually completely solved. So I'm not going to generalize this over arbitrary inner product spaces. So this is just looking at the dot product case for Cauchy-Schwarz inequality. Oh, shoot. I forgot to say one more thing. So equality occurs whenever they're linearly dependent. So one thing that you should observe here is that if we're going to partition these vertices, so remember, I'm avoiding a cycle of length 3 and 4, and I want the most number of edges. So one thing we can observe here first you may argue then, well, okay, this doesn't necessarily partition all the vertices of pairs. You could have even farther distance than just distance 3. So aren't you missing something? But what can we do here? If there were 2 vertices currently of distance 4, then this won't be the maximum possible, right? If I have these 4, this from here to here, the distance is 4, right? But I'm only avoiding a 3 or 4 cycle, so I always could have put an edge here. Right? So anytime if I were to see 2 vertices of distance 4, I could have put an edge here, and this is going to be a 5 cycle, avoiding still a 3 or 4. Right? So this would now increase the number of edges in the graph. So I guess I will have to briefly finish. The proof isn't very long, but I do want to finish it. So let me just write one more line here. So understand that when you're looking at these pairs, right, it should be clear these are all distinct pairs, right? You can't have 2 vertices having different distances. So if I were to look at the cardinality of all 3 of these sets, it should make up every possible pair of vertices, right? There can't be anything of distance beyond 3. Right. So yeah, I'm out of time. So I will finish this, I guess, on Friday. So it shouldn't take very long, like 10 or 15 minutes to prove. And then I'll just start reviewing on Friday and on Monday for the final. But a lot of you who have taken a class with me will see that we're basically leading into the Hoppen-Singleton theorem from this result. That's where everything is coming from, that we proved using eigenvalues in a different class. All right.
So
Are there any questions on that?
is this basically comes about because we can just represent our graph as a matrix, right?
What exactly do you mean by that?
Like I'm trying to imagine how, like, you know, we can think of as a function in Rn as like it's a matrix representation